Welcome to the last talk of this day. And well, first of all, let me let you know that these bottles of water are there on a purpose. Everybody has kicked the bottles. If you noticed, everybody kicked the bottles. But the reason why we have them there is that because you hit the bottles, you know that you're close to the edge. In that way, you don't have any accidents, hopefully. So they are there on purpose. Well, thank you very much for being here. It is a great pleasure for me and to introduce to you Professor Raul Gómez Muñoz. He is actually he's currently a professor at the National University of Nuevo León, but he was a former student of ours in Guanajuato, so we are very happy to have him here because there was a long time ago since the last time we saw each other, and it was very special for me to have him here in this meeting. Thank you very much for coming.
Okay, can you hear me? Is it working well? Yeah. What about now? Better? Okay. Yeah. Well, first of all, thank you, Adolfo, Isabel, and Mathew for the invitation. It is great to be here. It is great to see friends that I haven't seen in such a long time, and also to have the chance of meeting new people and hearing all of these interesting talks. And now I am supposed to give my own talk, and I'm afraid that it won't be as advanced or maybe as interesting as some of the other talks. But my idea is to give something more elementary and having a hope that maybe some graduate students and maybe some other students here could follow a little bit more of the talk. So I will introduce some new ideas, but it will be mostly stuff that the expert already knows. So an apologies in advance for that. So I hope that it is not too slow, but hopefully it will be enjoyable for everyone. Okay. So the title of the talk is Schwartz Functions and Intertwining Operators for Induced Representation of SL2, and this is part of a joint work with Burgess Peck. Let's start with the outline of the talk. So first, it will be divided in two parts. So the first one is going to be on Schwartz functions. So we're going to define the basic properties. First, I want to talk a little bit about semi-algebraic geometry, then introduce the notion of Nash manifolds, and then talk about Schwartz functions on Nash manifolds. And now, of course, this is a meeting on Lie theory, so we want to talk about Lie theory and representations. So I will say how these notions are used to define moderate growth representations for Lie groups. And in the second part, in part two, we will try to see some application of these methods to the study of some interesting representations. So as I said, that this is going to be a very basic talk. So I will start with induced representations of SL2R. It's the smallest interesting group. And then I will talk a little bit, if time permits, about invariant linear forms for PGL2R. That topic is a little bit more interesting, a little bit more new, but hopefully we will get there. Okay. Okay, so let's start with Schwartz functions on Nash manifolds. I want to talk about the definition and basic properties of this space, the space of Schwartz functions on Nash manifolds. I will follow mostly the presentation given by Asim-Vigurevich. Some of these ideas, especially with the point of view to representation theory, can be found in earlier work by Duclos. It is in French. We make it maybe a little bit less known than it should be. Okay, but I will be following mostly the Asim-Vigurevich presentation. So let's start with this definition, and this is a well-known definition. Given the real numbers, we define the Schwartz space. The Schwartz space for R is the space of all the functions that are smooth, and all its derivatives are rapidly decreasing, in the sense that you can hit it with any polynomial, and it's still going to be bounded. So the goal of this section is to extend this definition to more general classes of spaces. So of course, observe that in the above definition, it depends on being able to define polynomial functions on R. Right? I am defining these rapidly decreasing functions are the functions that decrease faster than any polynomial. So it is natural to restrict your attention to spaces with some sort of algebraic structure. I mean, you want to talk about what the polynomials should be on your space. Okay. And in this case, semi-algebraic geometry appears to be a natural framework here. At least it's the framework that has been working so far. Okay. So let's talk about semi-algebraic geometry. And given a subset of Rn, it is said to be semi-algebraic if and only if it can be presented as a finite union of sets defined by a finite number of polynomial equalities and inequalities. Okay. So why do you want to allow inequalities? I mean, like normally you have polynomial equalities, that's what you do in algebraic geometry. Here's an example. I mean, let's look at the set of all the x of y such that x squared plus y squared is actually, sorry. Yep. In part U, I have the set of all the x, y such that x squared plus y squared is less than 1, so we have like the unit ball. And this is like the usual open space. On the other hand, I have this other space. I have R greater or equal than 0. And this I see as, look at the curve y equal to x squared, and then take the projection onto the y-axis. So you are getting exactly this space. You're getting R greater or equal than 0. And of course, projection into the y-axis is a natural map. It's something that you would like to call a semi-algebraic map. So you would like the image of that map from this algebraic variety y equals to x squared to also be semi-algebraic. But in order to do that, you need to allow these inequalities. Otherwise, I mean, your category is not going to be nice enough. So given two semi-algebraic sets, X containing Rn and Y containing Rm, we said that a mapping F from X to Y is semi-algebraic if and only if its graph is a semi-algebraic subset of Rm plus M. And an example of a semi-algebraic function is the one that we have here. So I have the function f of x equals to 1 plus x squared, but I am taking the square root of this quantity. And as we can see, I mean, this is always well defined because I am working over the real numbers. And the point here is that this function is a semi-algebraic function, which is clearly not algebraic because I am taking this square root. So working with these semi-algebraic functions is giving me a little bit more flexibility. It is not as rigid as classical algebraic geometry. We have the following proposition. This says that semi-algebraic maps actually have very nice properties. In particular, they satisfy that the image of a semi-algebraic subset of Rn under a semi-algebraic map is semi-algebraic. And as we have seen, I mean, this depends on being able to use inequalities besides equalities to define our sets. The second one is that the closure of a semi-algebraic set is semi-algebraic. The composition of semi-algebraic functions is semi-algebraic. The R-value functions on a semi-algebraic set X, it forms a ring, and if you have a function that is nowhere vanishing on this set, then it is actually invertible. And finally, if I have a semi-algebraic set, and you have a semi-algebraic function, then you can find a polynomial function, an actual polynomial in your environment space in Rn, such that the values of f of x are going to be bounded by this polynomial function. So in this case, I mean, you have a well-defined notion of polynomial growth because you can compare with actual polynomials in the ambient space. Okay. So now let's talk about Nash manifolds. So a Nash manifold is a semi-algebraic subset of Rn, which is also smooth. It's also a smooth manifold. And we observe that if you have two open sets, two open semi-algebraic subsets, then a function is said to be Nash if it is smooth and it is semi-algebraic. So we have like this combination of the two words. We have like the smooth word and we have this semi-algebraic word, and we want them to play nicely with each other. Okay. Some remarks is that for Nash manifolds, we have an inverse function theorem. Right, so this is something that is definitely not true in algebraic varieties, and of course, I mean, a lot of the theory and the Tarko homology and all of these things comes strongly from not having this theorem and wanting to have it. In this case, we do have it. We have that the inverse function theorem, it holds for these maps between Nash manifolds. And the second thing is that the set of open semi-algebraic sets does not form a topology. And if you think about it, I mean, it is quite clear that this cannot be the case because as we have seen in one of the first examples, the open balls are semi-algebraic open sets. That means that if the semi-algebraic sets were to form a topology, then any open set in Rn will be semi-algebraic, which of course like kind of defeats the purpose. So unfortunately for semi-algebraic sets, we can take finite union of open sets. They are still going to be open and semi-algebraic, but we have to be careful about infinite unions. So we are normally going to use what is called a restricted topology. I mean, we're going to take unions of finite open sets, but we do not want to allow like infinite unions. Okay. We have the following classical theorem that says that a smooth manifold admits a Nash manifold structure if and only if it is diffeomorphic to the interior or some compact smooth manifold, possibly with boundary. So if you have a smooth manifold with boundary and you take the interior of that manifold, then it is a theorem that you can give it the structure of a semi-algebraic set. So I mean, like this theorem was, one direction was proved by Nash, and then the other direction, I forgot the name. But okay. Yep.
How unique is this Nash manifold structure? Because that might give you some difference on the growth of functions.
So the question is, if two manifolds are diffeomorphic, are they also like Nash isomorphic? Is that the question?
This Nash manifold structure on any smooth manifold with interior of a compact with boundary. Mm-hmm. Is this Nash manifold structure unique or not? Are there multiple choices?
See, I mean, So the thing is, I want to say that it is essentially unique, but we have to be careful with what I mean by that. Because, for example, let's think about the circle. So the circle, you can give it a structure as a semi-algebraic variety, as saying, okay, is the set corresponding to x squared plus y squared equal to 1? Okay, so that gives you a structure of this set as a semi-algebraic variety. On the other hand, you can also look at the projective space, let's say P1, which of course, I mean, algebraically is a completely different guy. And then when you look at the set of real points, then you're also getting the circle. So in that sense, if you see them as the space plus the algebraic structure, like the algebraic sheaf of regular functions and then the corresponding Nash manifolds, then it is highly non-unique. On the other hand, I mean, like the space of functions that you are actually interested in, like the space of functions that have moderate growth, the growth condition on your functions, those ones do not depend on this choice of algebraic structure. Okay. Okay, so now let's give this definition. So now that we have a Nash manifold, I want to give the definition of a Nash bundle. And of course, I mean, it is essentially the usual definition. A Nash bundle over X is going to be this 4-tuple where I have this projection of E onto X. I want this to be a surjective Nash map, but I also wanted it to satisfy the following two conditions. The first one is that each fiber has to be Nash diffeomorphic to Z. So in this case, Z is going to be my fiber. So I have like this typical bundle. I have E living on top of X, and every fiber is isomorphic to Z in the appropriate category. Of course, I want it to be Nash diffeomorphic to it. The second condition is that I wanted it to be semi-algebraically locally trivial. And let me explain what this condition means. What this means is that there exists a semi-algebraic open cover of X, and notice that this semi-algebraic open cover has to be finite. So normally when we are talking about bundles and all of these things, and we say, so you just cover it with some open sets, you don't care how many. But in this semi-algebraic setting, it is important that it is a finite number of open sets, otherwise we run into troubles. So we have this semi-algebraic open cover, and we have this trivializing isomorphism, which tells me that for every point, I mean for every one of these open sets, when I look at the inverse image, not only are all the fibers isomorphic to Z, they are isomorphic in a kind of a trivial way. They are actually isomorphic to UK cross Z. And once we have this definition of a bundle, then we can define a vector bundle over X to be simply a Nash bundle with linear fibers. And you want that all the trivializing maps are fibers linear, and you want all of these maps to be Nash. And given a Nash manifold and E a Nash bundle over X, we define a Nash section to be simply a map from X onto E that is also semi-algebraic and smooth. That is a Nash map. Okay. So these are the usual definitions, and the proposition is that with this natural definition, everything that you normally want it to be true, I mean, it is true. I mean, like the usual bundles are going to be Nash bundles. So the tangent normal, the tangent bundle, the normal bundle, bundle of densities, differential forms, I mean, all the usual geometry that you will do is going to be valid in this setting. So now let's make this definition. Given a Nash manifold, I define a Nash vector field to be a section of the tangent bundle of X. Right? So this is like the usual definition. That's how vector fields look like. And I define the algebra of Nash differential operators on X to be the subalgebra of this space, a space of homomorphism from infinity functions to infinity functions that is generated by Nash function and is generated by these section Nash sections, like these Nash vector fields. So it is like the natural definition. I mean, like you have the functions, you have the vector fields, and you are allowed to compose these operators as many times as you want, and you look at the corresponding algebra. Okay. And there is this lemma that tells me that any Nash derivation sends Nash functions to Nash functions. So of course, I mean, in the definition I was using C infinity functions. Well, I mean, of course, the natural space to look at will be the space of Nash functions, and yeah, it is a morphism from one to the other. Okay. So now let's talk about the space of Schwartz functions on a Nash manifold. So given a Nash manifold, I'm going to define the Schwartz functions on X to be the set of all the smooth functions on X such that df is bounded for all Nash differential operator D. And notice that this looks exactly as the definition for R. Essentially, I am saying I want a function that is smooth. And I want to be able to take all derivatives with polynomial coefficients. In this case, it will be like these Nash differential operators. And I want to make sure that this function is bounded on X. So it is exactly the same definition. Okay. And we have the following proposition that says that if X is a Nash manifold, then the Schwartz functions on X is a Frechet space, and it is also a nuclear space. So it has very nice topological properties. Okay. So given a Nash manifold, we say that a function f is said to be of moderate growth if for any Nash differential operator, there exists another Nash function h such that this df is bounded by h. And remember that if we think of our Nash manifolds as embedded in some ambient space Rn, being bound by a Nash function is exactly equivalent as being bound by some polynomial functions. So we should think of functions of moderate growth as functions that grow at polynomial speed. There is a polynomial, a fixed polynomial that bounds it. And then, of course, you can take derivatives, and then maybe you need to take a different polynomial that bounds it, but then you will always be able to find it. Okay. With the set of moderate growth functions, we will denote by Tx, T coming from temper. And the lemma is that if X is a Nash manifold, then the assignment U going to T of U defines a chief in the restricted topology on X. So remember, these semi-algebraic open sets do not form a topology. So of course, you cannot talk about sheaves if you do not have a topology, but I mean, like, you can just work your way around that. I mean, like, you can just say, oh, my open covers are going to be finite open covers, so you define this Grothendieck topology, and then you can define sheaves on that, and it looks exactly the same as the definition of sheaf. The only thing is that you have to be careful. You cannot take infinite union of open sets. You just have to take finite number at a time. We have also partition of unity. More specifically, we have this theorem. Given a semi-algebraic open cover of X, and notice again that I am taking this finite cover, so I always have to be careful with that. Then there exists some functions, alpha 1 to alpha m, temperate functions, such that they are supported on each of these open sets, and the sum of all of these functions is equal to 1. And even more, we can choose the alpha case in such a way that for any f that is a Schwartz functions, the product of alpha k with f is also a Schwartz functions. And notice that in general, for example, if x is not compact, the alpha case, you cannot expect them to be Schwartz functions, because at the end, I mean, like, you will have like this finite union of open sets, which says that at least one of them is going to be like not relatively compact, right? It's going to extend into infinity in all directions. And for that one, like these of these functions, I mean, like this sum of the k1 to m of alpha k, in order for that to be equal to 1, that means that the function corresponding to that open set, it has to be identically equal to 1 at the end. That is, it doesn't have like this rapidly decreasing condition. But on the other hand, I mean, you can choose it in such a way that it will preserve your space of Schwartz functions. If you have a Schwartz functions, you multiply by this alpha k, you have a sum of Schwartz functions on each of the uk's that adds to my function f. So we have the following theorem that tells me some very nice thing about these cocheif of Schwartz functions. So the first one is that if X is a compact Nash manifold, then the space of Schwartz functions on my space is actually the same as the space of C-infinity functions. So you are losing like pretty much no information. When you have a compact space and you talk about Schwartz functions, you are just talking about smooth, that's it. On the other hand, let's imagine that I have a Nash submanifold, and here it is important that I have like this Nash submanifold here. I mean, I will have one of the properties that I don't mention here is that Nash submanifold have tubular neighborhoods. So being embedded as a Nash manifold, it means that it is not embedded too widely. In any case, I look at the corresponding open set U and let U equal to X without Z, and then the space of Schwartz functions on U corresponds precisely to the space of all the functions in the Schwartz space of X, such that F and all its derivatives vanish at every point on Z. That is, it will be like the space such that 0 and all its derivatives are equal to 0. So an example will be look at R and look at the Schwartz space on R. Then what will be the Schwartz space on R star? It will be the space of all the functions whose value at 0 and the value of all its derivatives at 0 is just trivial. And that gives you immediately the definition of the Schwartz space for these other spaces. Yep. And we have Borel's lemma that tells me that if this Nash submanifold has codimension M in X, then we can look at the quotient of the space of Schwartz functions on X by the space of Schwartz functions on U, and it looks like Schwartz functions on Z that tensor with this power series, the Taylor series on X1 up to Xm. In other words, this quotient looks like Z. I mean, we have the Schwartz functions on Z, and you have this formal neighborhood, right? Like this ring of formal power series that go in the directions that are transverse to Z. So, as I was mentioning, an example here is the case where X is equal to R, C is just the origin, and in this case, if you look at the map that sends F to the Taylor series at the origin, then this gives me an isomorphism between this space SZ of X and the space of power series on X. And this is what Borel's lemma is telling me. I mean, it is clear that if I have a smooth function, then I can look at this Taylor series polynomial. What it is not so clear is that if I have a power series on X, the power series that might not be convergent, you still have a smooth function such that all its partial derivatives evaluated at the point give me precisely that power series. So that's like the hard part of the Borel lemma. Yep. So finally, let's just stick this together and put it in the concept or representations of Lie groups. So given a real algebraic group and be a locally compact topological vector space, a locally convex topological vector space, a representation pi b of G is said to be of moderate growth if for all seminorm Q of V, and of course all of these seminorms are continuous, and there is a seminorm Q tilde and a temper function on G such that when I look at this coefficient function, when I look at the norm of pi G of V, that's going to be bounded by this seminorm Q tilde evaluated at V and this function G. In other words, when I look at matrix coefficient functions of moderate growth representation, what I am getting is moderate growth functions, functions that have some kind of polynomial growth. And I should remark that if pi b is a representation of moderate growth, then V has a natural structure as an SG module under convolution. Having like, the matrix coefficient function have moderate growth means that whenever I multiply that function by a Schwartz function, I'm going to get another Schwartz function that I can just integrate out. And the second observation is that if G is reductive, then the above definition is completely equivalent to the classical Kasem-Wallah definition, and these are going to be functions that are like, smooth and moderate growth. Okay, so the advantage of this setting is that you can now look at some other groups, like some nilpotent groups, for example, even if you are just interested in reductive groups, you are always interested in the parabolic, nilpotent subgroups, etc. And in this case, you have this definition of what it means for a representation to be moderate growth. Good. Okay, so now let's switch topics. Now I want to apply a little bit of what we have seen so far, and I'm going to, as I said, I'm going to look at the most basic example. I'm going to look at the group G equal to SL2R, and I'm going to give a very, very explicit description. So I have G is equal to SL2R. I look at N to be this unipotent group is the set of unipotent triangular, hypertriangular matrices. A is going to be my space of diagonal matrices. And finally, K is going to be this maximal compact subgroup of SL2R. And in this case, they just correspond to rotations around the origin. Okay. So then the Iwasawa decomposition, that in this case can be just checked directly, tells me that G has a decomposition as K times A times N. And it should be more or less clear that the intersection of these groups is trivial. So we will take G to be the Lie algebra of G, the same for N and A. And I will choose these usual bases for SL2R, for the Lie algebra of G. And we notice that it satisfies the usual commutation relations. And the brackets are given by these formulas. Okay. And now I want to define the induced representations of SL2R. Okay, so I will take M to be this subgroup, like this group with two elements. This is just plus or minus the identity. And given epsilon, which is equal to plus or minus 1, I want to identify it with this representation of M that is associated to like this sign representation. So if epsilon is equal to minus 1, I want it to have the sign representation. If epsilon is equal to 1, then I just have the trivial representation of M. Okay. So once I have such an epsilon, and once I have a nu in A star on the dual of the Lie algebra of A, I will define the induced representation to be the space of all the small functions on G that satisfies this property. And of course, I mean N, M, G, N, A, M, and G are in the appropriate groups. And the property that I wanted to satisfy is that I have the A comes out as A to the nu plus 1, and I have the epsilon M. And this plus 1 is just some normalization to make like in some applications are easier. In this case, it is just such that when nu is equal to 0, this representation is going to be unitarizable. Okay, so given such an epsilon and such a nu, I have this induced representation. And what I want to do is study the structure of this I epsilon nu as a G module. And as I said, I mean, like this is going to be very, very basic. I mean, we will go very slowly. So we have induced representation. And whenever we have a family of representations for a group, there is like a natural question that we can ask. So the first one is, what is the structure of this induced representation of I epsilon nu as a vector space? The second question is, are the representations I epsilon nu irreducible? And the third one, are they equivalent? So I have this family of representations, and the natural question is, I mean, are these guys irreducible? If they are not irreducible, can you break it into smaller pieces? Second question is, if they assume like they are irreducible or not irreducible, whatever, are all of these representations actually different, or do you have isomorphisms between them, etc.? So let's start by looking at this space. We will start by looking at its structure as a K module. And we notice is that if we simply restrict our function to K, then according to the Iwasawa decomposition, this I epsilon nu is just look like the space of Schwartz functions on K with this epsilon condition. That is telling me that if epsilon is equal to 1, then I want to look at even functions. If epsilon is equal to -1, then I am looking at odd functions. So this is going to tell me, I mean, using this classical Fourier analysis, that I can break this space, the space of K finite vectors for I epsilon nu, which is the space such that, the space of all the functions, such that when I hit it with all the elements in K, and then I look at the span of that, I still get a finite dimensional space. And this is going to be generated by all the functions phi 2r plus epsilon nu, where phi r nu is given by this formula. So of course, I mean, I want it to be induced functions. So of course, like the value for A is no surprise. And then for k theta, I am simply looking at the e to the I r theta. Okay. So now let's look at these other bases for SL2R. So I am looking at these bases E, H, and F. And these bases also satisfies the usual commutation relations for a basis of SL2R. And we notice that the phi RV are actually eigenvalues for the action of H. I mean, like this element H, when I multiply by I, it gives me the matrix 0, 1, minus 1, 0, which integrates precisely to the group K. And from this relation, it also follows that if I hit phi r nu by E and then I hit it with H, then I use my commutation relations to get that what I get is an eigenvalue, an eigenvector with eigenvalue r plus 2. In other words, this E of phi r nu is going to be some constants times the function phi of r plus 2 nu. And we can actually compute this constant C of r nu pretty straightforwardly. What we do is we notice that I can rewrite this operator E as H plus little h minus 2IE divided by 2. So you simply do it that way. And when you add with this operator on a function f and you just evaluate it at the identity, you get precisely the constant that you want to compute. And in this case, the constant is nu plus r plus 1 over 2. Okay. In a similar way, if I hit it with the operator f and I have this phi r of nu, I'm going to get a multiple of phi r minus 2 of nu, and I have these constants. And notice that these coefficients that we have here, they are going to be 0. They only have a hope of being 0 whenever nu is an integer. Otherwise, I mean, they just keep going forever. Which just tells me how to analyze the structure, how to analyze the irreducibility of these induced representations. So, besides using these formulas, it is possible to analyze the reducibility of I epsilon nu of K. K is a space of finite vectors as a module for both G and K. That is, it's structured as a GK module. So normally when you're looking at the structure of infinite dimensional representations of a Lie group, the space can be very complicated topologically. So in order to make it simpler, in order to make it more algebraic, you look at the space of K finite vectors, as we have done here, and then we look at the action of the Lie algebra on this space. And that allows you to get a better insight into the structure of your representation. So in this case, we have the following result. We define DL plus and DL minus to be the holomorphic and anti-holomorphic discrete series of SL2R. The DL plus consists of all the phi R such that this R is greater or equal than L plus 1. For the DL minus, we go in the opposite direction. We are taking starting from minus L plus 1, and we let FL to be the guys that are between minus L plus 1 and L minus 1. And we notice that since these E and F are moving our operators in 2 by 2, this is simply an L-dimensional representation. Okay. So this is the composition of induced representation. If nu equal to L is a positive integer and the epsilon is congruent with L minus 1 modulo 2, then we have this decomposition. My representation I epsilon L K is not going to be reducible. It's going to have this subspace of DL plus direct sum DL minus. These two are irreducible. And it's going to have an irreducible quotient, which is this finite dimensional representation. If nu is equal to minus L, if in this case this is a negative integer and I have this epsilon congruent with L minus 1 modulo 2, then the situation flips. So in this case, the finite dimensional representation is going to be a submodule of the induced representation, and when I take the quotient, I have the direct sum of the two discrete series. And in all other cases that we have seen, I mean, like all of these operators, E and F, they will simply generate my whole module, so they are all going to be irreducible. Okay. So now we want to move to the third topic. So we have seen how the I epsilon nu look like. I mean, they are generated by this specific function that we wrote down. We have looked at this representation. We know when they are irreducible, and when they are not irreducible, we have found its composition series. So now the last question is whether or not these two representations are equivalent. And let me just make this very quick observation here. So let's imagine that I have V a G module, and I have an intertwining map from B into some induced representation I epsilon nu. This space I epsilon nu has a natural map to the complex numbers, which is simply given by taking a function phi here, and then taking that to the value of phi evaluated at the identity. So of course this map is not going to be G equivariant. However, it's definitely going to be N equivariant. I mean, this function is induced representation. So when I evaluate at E and I hit it with an element on N, it's simply going to come out trivially. That means that every time that you have an embedding of V into one of these induced representations, you get by free an N invariant linear map. Okay, so on the other hand, whenever you have an N-invariant linear map, you can try to repeat this construction. You can try to turn this construction around to get an embedding into an induced representation. So the way we are going to study the maps between these two different induced representations and check if they are equivalent is look at the space of N invariant linear functions, the space of N covariance in this case, and then try to figure out from there which one of these maps actually come from intertwiners between them. Okay. So we start with recalling that if we take W to be this element in G, then we have a Bruhat decomposition of SL2R given in this way. So G can be written as P union PWN. Notice I am just only using N on the right. P is simply the product of M, A, and N. And we take U epsilon nu to be the space of all the phis in I epsilon nu such that phi and all its derivatives vanish at the identity. So remember, I mean, this space we have seen before, this will be precisely the Schwartz space of all the functions that are like corresponds to the open set where we take away the identity in my group G. Okay. And we will take W epsilon nu to be the quotient of this space, the I epsilon nu, that remember is simply the Schwartz functions on the space K, modulo these open sets. And we already know what is the structure of this quotient going to be. It's simply going to be power series is evaluated at the identity. So given a phi in I epsilon nu, I'm going to define T0 phi of x by this formula, and I'm going to define T infinity phi of y by this other formula. So what I am really doing here is the following. So I am looking at K here, and I am taking W, W here at the bottom, and I am taking the identity here at the top. So I am seeing at this space as the projective space, and I am identifying W with 0, E with infinity. And the observation, that is also pretty straightforward, is that if I do T0 of f phi evaluated at x, this is exactly the same as the derivative with respect to x of T0 phi of x. And similarly, if I do T infinity of E phi of x, this is going to be the derivative with respect to x of T infinity of phi of x. Right? Because we know that here at the identity, here with E does nothing, because I know that the action of n around the identity is simply trivial. This is an induced representation. And the same thing happens at W, but now with the F replaced by the E. Okay. So then we have the following exact sequence. So I have the U epsilon nu, the I epsilon nu, and the W epsilon nu. They form an exact sequence because I just defined W to be the quotient of the first two. And what I want to look at this exact sequence. So I am interested in the space of covariance. I am interested in the space of covariance of the function of the guy that is here in the middle. And I would like to say, oh, that should be just like the sum of the invariance of this space that is very easy to compute and the invariance of this space that is very easy to compute. And it would be great if that were the case. The problem is that sometimes life is not so nice and you have like these homology groups getting in the way. So what I want to do in order to compute this space of covariance, this jacket module, is of course computing this guy, and I will also like to compute this connection homomorphism. In that way, this connection homomorphism is giving me the obstruction from extending a linear functional defined here in U epsilon nu to a linear functional on my whole space. In other words, these linear functionals in U epsilon nu that are n invariants are normally going to be defined by just integration over n. And that's pretty simple, and because I am restricting myself to Schwartz functions, everything is fine. But when I look at that, at all the functions on I epsilon nu, I do not only have the ones that vanish at infinity. I have guys that have a very specific growth, a very specific behavior at infinity. And the question is, when can I extend this integral from the space of Schwartz functions to the whole space? Right? So is there any obstruction for me being able to do this? And this obstruction is calculated precisely here in this connecting homomorphism. Okay. And observe that also in this case the first homology of W epsilon nu is given by the space of invariance, and that's because n is one-dimensional. So normally to compute the Lie algebra homology of a module, you need to write down the Koszul resolution, but if n is one-dimensional, the Koszul resolution is very simple. Is Koszul resolution is given by, so I will have 0, and then I have the tensor product of n with b, and I have a map to V, and then this goes to 0. And this is simply take an element on the Lie algebra, take a vector on V, and I will simply take it to the action of x to V, which tells me that the first homology of n with coefficients on V is simply the space of invariant, and the 0 homology of n with coefficients on V is simply the space of covariance. So in this specific case, because my Lie algebra is just one-dimensional, it is trivial to compute these spaces. So we want to describe all of these spaces appearing in the sequence, and I want to describe the corresponding connecting homomorphism. Okay. So the first observation is that this map, the map phi going to T0 of phi, defines an isomorphism between the space of functions in U epsilon nu and the Schwartz space of R. And that's because this space essentially is giving me identification of R with the space of all the points here in K without the identity. So of course that just looks like the Schwartz functions on R, and we have seen that the space of Schwartz functions corresponds precisely to the space of functions that vanish identically on this closed set, and in this case my closed set is the identity. On the other hand, if I look at the map phi going to all the Taylor series at infinity, at my point E, then this is going to give me an isomorphism between W epsilon nu and the space of sequences of complex numbers that are endowed with the projective limit topology. And remember, I am taking these f's because f corresponds to taking partial derivatives over there. I probably wrote it wrong. Yeah, I wrote this. Sorry. We have this wrong. This is the infinity, and this is the 0. So this is the 0, and this is the infinity. And furthermore, we have this action. So when I look at the action of E of fk of phi, I have this number. I have minus k to the nu plus k f to the k minus 1 phi of E. In other words, I have all of these guys. I have the t infinity at 0, and then I apply 1 times f, and applies 2 times f, etc. Now, if I hit this function by E first, what I am doing is I am simply moving from here to there. I am moving like one guy to the left. So I will always have one guy that is just going to 0. I mean, like this one is just going to 0. But then for the otherwise, they are going to be 0. I'm going to have another element in the kernel if and only if this quantity here is 0. But of course, this quantity here is going to be 0 if and only if nu plus k is equal to 0, which is precisely the case where I have representations I epsilon nu that are not irreducible. So at that specific points is where I am seeing something happening with my space. Okay. As a corollary, I mean, these maps induce an isomorphism between space of covariance in U epsilon nu with the complex numbers. As I said, in this case, my invariant linear functional is just simply given by integration over n. Because these are Schwartz functions, I have absolutely no issues of convergence. And the dimension of this W epsilon nu, as I said, this is going to be 1 if nu is not a negative integer, and is going to be equal to 2 otherwise. In other words, I mean, the distribution that are like kind of supported of that corresponds to my open orbit here under the Bruja decomposition. They are just given by integration over the orbit. And we have more invariant operators that just corresponds to evaluation at the identity. And we may have another one, which is take a given number of derivatives and then evaluate at the identity. But that only happens when k is a negative integer. That only happens when this quantity that we have in these slides before, this quantity here, is equal to 0. Okay. And conversely, the dimension of the space of invariance is going to be 0 in general. It's going to be 0 if nu is not a negative integer, but it's going to be 1 otherwise. Notice this correspondence. This is telling me that in general, I will have this space, the invariant linear functional that corresponds to simply taking my induced representation. I just evaluate at the identity. That will always give me an n invariant linear functional. In order to find the other ones, what I do is I look at this integral for Schwartz functions on this open cell, and then I ask whether or not I can extend this to a linear function over my whole space. And notice that when I have extra candidates, when I have extra guys to put it on the closed orbit, that's precisely where I could have an obstruction for my integral to extend to an integral to the whole space, to a linear functional on the whole of my induced representation. So first, just a quick remark. The relation between this T0 and T infinity of phi is that they are related by this formula. They are essentially one is the inverse of the other. But what we have is a bundle on this P1 of R. So I need to twist by this extra parameter. So in particular, when nu is a negative integer, it is equal to minus k. And I choose 2 infinity epsilon nu of x to be this operator. Then when I twist it and when I see it from the point of view of 0, everything is going to cancel. I will have like this number coming from above, and then my definition is x to the k minus 1 is this guy over here, and I just get the sign guy. So in other words, this guy, the x to the k minus 1, this is precisely the guy that corresponds to my extra differential operator on E. It's going to be the guy such that when I take k minus 1 derivative and I evaluate at 0, it is non-zero. But when I see it from the other point of view, when I see it as a function here in this neighborhood, my function looks like this. I have 2 options. It either looks like this, and then it just joins some way, or maybe it looks like 1 and 1, in which case I could just simply connect directly. So I have, at infinity, I just see the same thing. I'm just seeing polynomial functions on k, but on the other hand, when I am seeing them here from 0, what I know is its behavior as it goes to infinity, and it just looks completely constant. The thing is that in this case, the 2 values agree. In the other case, depending on the value of the epsilon, the 2 values are different. Okay. So essentially, we have proved the following integer. If phi is such that when I look at the behavior around the identity, it looks like y to the k minus 1. Then in this case, the space of invariant functions on W epsilon nu is generated by precisely this guy, by precisely this polynomial function. And for such a phi, when I see it from the other point of view, when I see it around a neighborhood of infinity, but more like when as x goes to infinity, then it just looks like the sine function to the epsilon minus k plus 1. Okay. So this is telling me that in order to compute the connecting homomorphism, in order to find the obstruction for this integral operator to extend to the whole space, what I need to do is find the class of the boundary of phi in u epsilon minus k. But this corresponds to taking the derivative of my function and then apply my only operator in u epsilon minus k, which is integration over r. And when I do this integral, what I am doing is I am taking derivatives, and then I take the integral from minus infinity to infinity. So of course, when I take derivatives of these functions, which are constant equal to 1, they just vanish at infinity. But then when I integrate over, I have that the only thing that matters is the behavior at minus infinity at infinity. So it doesn't matter how I connect these 2 guys. If I take the derivative and then I integrate, I will always get 2. On the other hand, for these guys, when I take the derivative, this function vanishes completely, so when I integrate it, I will get 0. So this is telling me precisely when I can extend my integral over the open cell to an operator over the whole space, and when I actually get an obstruction. Okay. So if we put everything together, what we have is that the dimension of this space, the dimension of the I epsilon minus kn, is equal to 3 when these conditions are satisfied, when I have epsilon equal to k minus 1 modulo 2, and it is equal to 2 otherwise. Okay. So I just wanted to tie this together, what I was saying here about like these intertwining operators. So in general, when I have a phi in I epsilon nu, we define its jacket integral to be this integral that we have defined here. So I have the integral minus infinity infinity of this function. I am simply integrating over n. Okay. And we define the Napstein intertwining operator by this formula. So essentially, if I have a function phi and I want to intertwine and I want to see it as an element of a different induced representation, what I do is I hit my function phi with g and then I apply my Jacquet integral. So that's guys are going to be the guys that are going to give me a math between the I epsilon nu and the I epsilon minus nu. Those are the answer to my last question. They are going to be equivalent whenever this Napstein integral makes sense. Now remember, we have been computing, this space of induced representations and these n modules precisely to know when this integral extends from the space of Schwartz functions to the whole space. That is, this Napstein intertwining operator is only going to work when I have no obstructions, when I have like this condition, this parity condition for the epsilon and the k. Okay. We have this lemma, this Jacquet integral, it converges absolutely for the real part of nu bigger than 0, and it actually has a meromorphic continuation to the whole of A star. And a point of the theory here, the point of this Napstein integral is to figure out exactly where the poles are and how they are resolved and what other operators you get in that cases. Okay, so if nu is not an integer, or if nu is congruent with epsilon modulo 2, then we know that this guy is irreducible, and this guy is going to define an intertwining isomorphism. So for the space of functions that vanishes completely at E, we know that we simply have to integrate. For the other guys, we know that this integral has a unique extension. That's the computation that we have been doing. Okay. I want to look at this special case that is a little bit curious. So I'm going to look at the representation I1 nu. So in this case, I have like the trivial representation. I am saying these are even functions on K, and I just let my parameter nu move around. And I will have this special guy. I will just have the guy that is the identity on the whole of K. Okay. And if I compute the Jacquet integral, I can just do the computation explicitly, and then I recognize this integral here as the beta function at nu over 2 and 1/2, right? So it can be expressed as a quotient of gamma functions. And this function has a simple pole when nu is equal to 0. So in this case, this integral just doesn't work. It doesn't give me an intertwining map between the two induced representations. And if you think about it, that is natural. When nu is equal to 0, I will have I1, 0, which is an irreducible representation. And normally, I will have the Napstein map that is going to be an intertwiner between the I epsilon nu and the I epsilon minus nu. But of course, when nu is equal to 0, nu and minus nu are the same, so I should not get anything new. So I will only have one intertwining operator between I epsilon 0 and I1 0 and itself, and it will just given by evaluation at 0 because that clearly works. Okay, so this is natural that we have a pole here. On the other hand, when we computed the space of n covariance, that space actually has dimension 2. So I have the one guy, which is evaluation and identity. We know that the Napstein cannot be because it just simply has a pole there and it just blows up, but we are still getting another guy. And it is kind of weird because you will expect this guy to define an intertwiner, but we know that there are no more intertwiners. So what is happening here is that we can define this other operator. So in this case, I have the Jacquet integral, and I modify it by this multiple of the delta function at the identity. And the point of doing this is that I am pretty much eliminating one of the poles. I used to have a pole of 0. Now I have moved my pole to -1 because this number and this number are going to cancel when I evaluate to this function that is identically equal to 1. For such a nu, this space, like the space of n invariant linear functional, is going to be generated by these two guys. Normally, I was taking the basis that is evaluation like delta the identity and then the Jacquet integral. In this case, I am using this k. And the reason is that if I write down the action of H, the action of my group A with respect to this basis, it looks like this. So for delta E, it is an eigenvector, which tells me that, yes, evaluating at identity is precisely an intertwiner. For the K1 nu, we get like this more complicated formula. In particular, if I look at the associated matrix, it has this form. And normally for the values of nu that is different than 0, these two values are different, so this value here is irrelevant. You can just diagonalize your matrix and get from these two invariant linear functionals to get two intertwining operators. But when nu is equal to 0, I actually get this matrix. So the guy corresponding to this guy, this is simply evaluation at the origin. That's the intertwining that we used to have. This other guy that we have here is our k. This k is an n-invariant linear functional that is not an intertwiner because it is not an eigenvalue for the action of A. In that case, I mean, we have this upper triangular matrix. So that's the reason why we have two n-invariant linear functionals, but only one of them can define an intertwining operator. Okay. So have to 6:30. Okay, so now let's move to another application. This is going to be pretty similar to the analysis of the induced representation of SL2R. It's just that things are going to be a little bit more complicated. Now what I want to do is look at the space of invariant trilinear forms on induced representations of PGL2R. And I mean, this space of induced representation, I mean, they have a long history. They were first studied by Bernstein and Rezhnikov, and with a view in application to number theory. Essentially, they wanted to have bounds for some automorphic forms. And the way they found the form, the bound, is that they simply wrote down the automorphic form down. It says, I mean, this is the automorphic form, so I can just compute it, I can just bound it because I know what it is. Okay, and that's why they were looking at these invariant trilinear forms. Okay, and later, Claire, Kobayashi, Oster, and Pesner, they analyzed this structure of triple tensor product for induced representation, but they added some other group, like for example, ON1 and some more complicated stuff. And the relevant bibliography is here. These are the relevant papers. Okay. In any case, let's start with G equal to PGL2R, and of course, I mean, I want to define again everything. So in this case, I will have my N, it is this space, this group. M is now this group. Now notice that this example is slightly different. I am looking at PGL2R, which is actually not connected, and it has no center. So even though the M is like the same letter, it's slightly different group. Okay. A is given in this form. And I have P equal to MAN, and we have the corresponding Lie algebras. Okay. And I will set K naught to be the identity component of the maximal compact subgroup. So my group G is not connected, which means that my maximal compact also has to be not connected. And essentially, I am just missing the guy 0, 1, 1, 0, the guys of determinant -1. So we take the W to be the same guy as before, and we define induced representations in pretty much the same way, just with the observation that in this case my M is slightly different, but it's still a group of order 2. Of C infinity functions in K naught. And what I want to do now is to compute the space of invariant forms on the triple tensor product of induced representation. So I have an action of P in the triple tensor product of these guys. And by Frobenius reciprocity, I can immediately reduce these to simply looking at invariant linear functionals for P. That is P here. So what I am doing essentially is I am taking at the last guy. The last guy is an induced representation from G to P, and I use Frobenius reciprocity there to say, oh, okay, I can just look at complex value functions here with a twisted action of A, and just reduce the dimension of my problem by 1. So I will concentrate on the space on the right. The first thing is that I want to describe what the action of my group looks like, because I have used this Frobenius reciprocity, so I just need to normalize everything. So in this case, I see that the space of functions that satisfies this condition. And the P action is just given in this way. So notice that I am acting on the right, where it is MAN, but I also have to ask this twisting coming from the third component. And now observe that since this K0 acts simply transitively this P1. P1 is my projective space. Then as vector spaces, this just looks like the space of C-infinity functions on K0 cross K0, which looks like the cross product of two projective lines. Okay. So now we want to decompose these two copies of the projective line under the action of P, and it's going to decompose into three orbits. So one is going to be the open orbit, the orbit where these X and Y are just different than 0 and they are all different. And then we're going to have two orbits in the middle. It is one is when I have infinity on one guy, the other is when I have infinity on the other guy, and the other one where the two X and Y's are actually equal. So these two orbits are going to be one-dimensionals, and I'm going to have a smaller orbit, a zero-dimensional orbit that is just given by the point infinity, infinity. Okay. So this O0 is the only open orbit, OC is the only closed orbit. And we have the corresponding dimension. The open orbit has dimension 2, these intermediate orbits have dimension 1, and the closed orbit has dimension 0. I'm going to repeat a little bit of the computation that I just want to give an outline of how this looks like. So we look at the space of functions such that f and all its derivatives of size of this is going to look like the space of Schwartz functions on my orbit O0. And notice that in this case, I mean, the O0 is going to be some Nash manifold, so I really need this theory of Schwartz functions on Nash manifold to completely make sense of these computations. So then I look at UC. This is the space where f and all its derivatives vanished outside the closed orbit. Outside the closed orbit. In other words, I mean, the relation between these two is like this is the open orbit, then this UC is like my whole space. I am just taking the point infinity, infinity away. Okay. And the BJs are going to be the guys such that f and all its derivatives vanish outside the union of an open orbit with one of these intermediate orbits. Okay. And we will take the corresponding quotients, these WJs, and this will give me the exact sequences just as before. And just as before, the spaces I am actually interested in is this V here. And of course, I would like to say that the invariant functionals on B are just going to be the sum of the invariant functionals here and the invariant functionals there, except that we have homological issues. So if we look at the space of P covariant vectors, we have the following exact sequences. So our idea to describe this space BP will be to look at the corresponding WP sharp, UP sharp, and look at the corresponding connecting homomorphisms, and try to, at the end to compute to see like which integrals can be extended to the whole space, which integrals cannot. And I should remark, I mean, like the guy supported in the open orbit is going to give me an explicit integral. This was the integral that was explicitly computed by Penstern and Reznikov, and there is like a precise formula telling you how the kernel of the distribution looks like. Yep. So we have the following lemma. So I have this map that goes from B3 to S, and is given in the following way. Remember, B3 is the space of the open orbit plus the third intermediate orbit. So this looks like an isomorphism. I mean, this gives me an isomorphism between the space of n covariance and the space of Schwartz functions on R. And furthermore, like the image of U0 which is contained in this B3, is precisely the Schwartz functions on R star. So when I take n covariance, I am just seeing, I am just reducing, I just integrating the action of n is free there, so I can just integrate out to get functions on R, modulo functions on R star. So this exact sequence remains exact after taking covariance, and it actually looks like this one. And we have already analyzed this space S0 of R. It just looks like Taylor series at 0. Okay. And even more, I want to describe the action of AM on Vn. This action is going to be given by the following formula. So I will have sigma A is going to be like this twisted action. So I have the usual action of A on R star, where I need to add this twisting that, of course, is coming from taking all of these tensor products and all of these simplifications and then taking all the integrals and everything else. Finally, the action of M is given by this formula. And I will take epsilon to be the sum of all the epsilon 1, epsilon 2, and epsilon 3. And I will look at the Schwartz functions on R, and I will divide it into the even ones and the odd ones. Okay, so just as I did before, we define similarly the S epsilon R star and the S epsilon 0 of R. Okay, so now we have this sequence. So I know that after taking n covariance, my sequence remained exact. Here I have no cohomology. So I have now this sequence, and these guys are going to be A modules. And now I want to take A covariance. And that's where I will want to have, I might have a homology, and where I will need to compute the corresponding connecting homomorphism. So given an f in S epsilon R, I define this operator, which is simply given by integration over R star. So this is now the guy that might create me problems. I know that these functions vanish identically at 0, so it doesn't matter what polynomial I choose here, this guy will always integrate out. But of course, if this function does not vanish at 0, and then I have this guy to be like a negative integer power, then I have poles. Okay. So this guy induces an isomorphism between this space, the space S epsilon R star A, and the complex numbers, and it has trivial one homology. Okay. On the other hand, if epsilon is even, then I will just look at the even terms in the Taylor series expansion of my functions, because those are going to be the only ones that survive. And this gives me an isomorphism between this epsilon, S epsilon 0 R and the product, this projective product of sequences in C. This space, the last space is endowed with the projective limit topology. Okay. And similarly, if epsilon is odd, then I will just look at the odd terms in the Taylor series expansion, and this will give me an isomorphism between this S epsilon 0 and the same space on the right. So again, we take the last space and endow it with the projective limit topology. Okay. So the dilemma is that for all f in S epsilon R, and all A in A, this action, the sigma A F L, L, this means taking L derivatives of my function at 0, and the action is given in this way. It's just given by this number. And remember, I want to look at the guys that are invariant under the action of this A. And that is going to happen if and only if this number that we have here on top is actually equal to 0. So that's going to give me the invariants. They're going to give me the guys that are going to become obstructions for me to extend my integral. Yeah. So as a corollary of that, I get that the zero homology of this space of H0A S epsilon R is going to be equal to the complex numbers if L is congruent with epsilon modulo 2, and nu 3, which is written in this way, can be written in this specific way where L is a natural number. Otherwise, I will 0. But even more, the first homology of this epsilon S epsilon 0 and the 0 homology are the same. So in other words, once again, every time that I have an extra operator, in this case supported at the 0, I will also get an obstruction. And it will be exactly pretty much the same function, that is an invariant and a covariant, because this action of A turns out to be semi-simple. So when we are looking at this sequence, the sequence when I have H1 of A, S epsilon of R, all the subsequences they go into this first covariant. Remember the guy that we are interested in computing is this connecting homomorphism. Then I will have these two guys are isomorphic, and even more, the boundary map is always non-trivial when these spaces are isomorphic. So in this case, you get that the dimension of this space of H0A S epsilon R is always equal to 1. Okay. And for the proof, what we do is pretty much the same as we did before. I will just show you a little bit of the computations. I don't want to go too much into the details. It is just the same idea. I will take take f of x to be this polynomial function. This is a well-defined function in a neighborhood of the origin, and it's going to be Schwartz once we kill it at the infinity. But we don't really care at the behavior at infinity at this point. Okay, and we look at these differential operators. So this is the differential operator that is going to correspond to the connecting homomorphism from the H1 to the H0. Okay. And in a neighborhood of 0, if I apply this differential operator here, I will get 0 because this nu 3 minus nu 1 minus nu 2 plus rho is precisely equal to L. So we just need to check that when I apply this differential, so it says it is straightforward to check that this D, like this differential operator that we had before, as I said, it induced the connecting homomorphism delta. And the class of F can be taken as a generator for this H1A S epsilon 0R. So what we want to show in order to prove the lemma is that when I apply my invariant operator to the function df, I will get something non-zero. I will get an actual obstruction. So we just do the computation. And again, I mean, this is the integral over R star of this differential operator applied to F. But then we notice that this guy looks precisely like the derivative with respect to a of this function, a to the nu 3 minus nu 1 minus nu 2 plus rho of f to the a minus 1. And once again, I have the integral over the derivative, which means that I just need to evaluate at infinity and at 0. And of course, I don't know exactly what my function f looks like infinity, but we know that it is a Schwartz function, so it has to vanish. And the value at 0 with all the appropriate derivatives, that we already computed. And in this case, this is precisely equal to minus 1, which is, of course, different than 0. So the observation is that if we alternate the roles of the I epsilon 1 nu 1, the I epsilon 2 nu 2, and the I epsilon 3 nu 3, we can get similar conditions for the existence of Euler linear operations supported on the other two intermediate orbits. Okay? So we have the big orbit. On the big orbit, we only have like this big integral, and now we have been able to find what are the conditions under which this integral can extend to the intermediate guys. And what we have obtained so far is that whenever you have any invariant linear functional that is supported in any of these intermediate orbits, the big integral just collapses. It just ceases to exist. And in more like traditional terms, what we'll get is a resolution of your pole. I mean, you have this integral operator defined on this open orbit. It will have some open set on which it is absolutely convergent, and it will have meromorphic continuation to the whole space. And then, of course, at some point you will have poles, but when you resolve those poles, you expect to get new intertwining operators. These poles occur precisely when you get operators supported on the intermediate orbits. And every time that happens, the orbit collapses. The orbit goes to infinity, you need to resolve the pole and get the corresponding intermediate guy. So using this information, we can easily compute the space of p-invariant linear functionals on this space. This you see is the union of the open orbit and the three intermediate ones. So the only thing that we're missing is the infinity point on top. We're just missing the point at the top. Okay. Okay, so similar but more complicated computations can be done with a closed orbit. I mean, the computations I don't want to show here because I mean they are a lot more complicated, especially going from the closed orbit to the open orbit, like this two-dimensional jump. It is way more complicated, and it is just pretty much the same idea. I mean, finding the corresponding homology guys, like finding representatives, calculating the derivative, and then computing the integral. So it is just the same thing. It's just with the uglier functions. But we want to describe what is the finite answer, like what is this space of invariant trilinear operators. So let me write down these conditions. So I'm going to set alpha to be minus nu 1 plus nu 2 plus nu 3. Alpha 2 is nu 1 minus nu 2 plus nu 3. Alpha 3 is nu 1 plus nu 2 minus nu 3. Delta is these guys. So we are looking for these conditions. I want when alpha 1 is an integer, alpha 2 is an odd integer, alpha 3 is an odd integer, and I need to have like this congruence modulo 2 or I will have delta equals to -2 and -1. So these three guys, at least like the condition for the alpha 3 we have seen before. This was the condition for being able to have a invariant linear function. So this one is delta equals to -2 and -1. This one corresponds to having invariant differential operators supported on this closed orbit. So when we have when these conditions are satisfied, then we're getting new invariant operators are supported there, and it could even be just like evaluation of the identity or taking derivatives in any of the two transfer directions. Okay. So with these conditions, we have the following results. So let me explain what this means. So the number of plus and minus denotes the number of elements among the nu1, nu2, and nu3 that are positive or negative integers. So at the end, I mean, like the answer, of course, depends on the behavior of the I epsilon nu as an induced representation. We know for integers, it is when this representation cannot be irreducible. Okay. So it tells me how many of these guys are positive or negative. And this column defines the number of conditions that are being satisfied. So remember, I wrote 4 conditions, and I can have no condition, 1 condition, 2 condition, 3 condition. And it is impossible for parity reasons to have the 4 conditions satisfied. I mean, just like the epsilon just cannot match. Okay. So in that case, if we have like no condition satisfied, then I can compute the space of invariant linear functionals. And the star means that these conditions cannot be fulfilled. So in this case, it is not possible for me to have no new two are not and satisfies more than 1 condition. Whenever I have more than 2 conditions, I automatically can solve for either u1, u2, and u3 to be an integer. This double star is more particular. For that one, we have to be more careful. And it happens precisely when my 3 parameters, u1 and u3 and u3, are negative integers. Number of invariant linear functional is normally going to be 2, but it's going to be 3 if these side conditions are satisfied. I want u1 bigger than the sum of u2 plus u3, u2 has to be bigger than the sum of u1 plus u3, and u3 bigger than the sum of u1 plus u2. So whenever these conditions are satisfied, I am getting an extra invariant form. And actually, this is what functionals that are supported on this infinity point. And when these conditions are satisfied, then the integral of does not have a port. Option for being sent to the whole space. And that gives me the third invariant linear functions. So I think that this is all I have ready for today. So thank you very much.
Are there any questions? Comments?
SL2.
Yes.
Now, representations I'm familiar with were developed by Valentin Bargmann, and there are 3 representation series. However, I mean, the principal series is discrete and exceptional. Or if you follow the Russian school of Gelfand, the supplementary, complementary, and principal.
Yes.
I couldn't see representations with which I'm familiar.
Yeah. So I guess you have like the principal series representations. They correspond to the guy where the epsilon is equal to 0. Now, where epsilon is equal to 0, so we go. Well, it will be quite a bit. So maybe we can talk when I click. You're talking about unitarizable representation. I general family of representations. So in this case, I mean, when I am defining these guys, the I epsilon nu should be close. In case.
That's at the very beginning.
Yeah, here. So I am defining these guys, like the I epsilon nu, sorry, it should be here. Okay, so notice that in this I have two parameters. I have the epsilon and I have the nu. Now, when nu is purely imaginary and epsilon is equal to serial representation, and that one is a family of unitary representations. In the epsilon is equal to 0, I am allowing nu to be a number. So my representations are not going to be unitarizable. I'm still talking by the microphone. Okay. But for all the other guys, those are not going to be in this principal family. Then you have the other family, which is with epsilon is equal to 1. And you again have like the imaginary axis with nu equal to 0. And the complementary family, they correspond to guys where nu is between 0 and 1. So those are different because it is not automatic that those guys are going to be unitarizable. I mean, the usual inner product, the one can think about it, it is not unitary. But one can twist that product and make it unitary. So these complementary series are precisely the guys where nu is between 0 and 1. And that is the complementary series. And the discrete series is what I call here the holomorphic and anti-holomorphic.
Discrete term is lower bound.
Yes, that's right. So that's why, as you can see here, the R is bounded by below, and in this case, the R is bounded by above.
Now, also representations of the covering algebra, or well, the covering group.
Yes.
And you can have indecomposable representations. Mm-hmm. And of course, also finite dimensional ones. You have all of them here.
No, so in this case, we were only looking at representations of PGL2R. I mean, like the SL2R is an easier example to look at because, I mean, it's a very nice group. We were actually looking at this triple tensor product of representations of PGL2R. So in this case, I mean, like the action of the center is just completely mapped out. So we are definitely not looking at covers. But definitely, I mean, looking at covers and all of these representations, associated representations, will be something interesting to look at. I mean, we are looking for more examples to apply this technique to.
Yeah, I just wanted to remark that the 2+1 Lorentz group has many realizations beside representations. And it's also the symplectic, the lowest symplectic group. Yeah. So I think it's a very important algebraic group.
Yeah, no, for sure. I mean, definitely, I mean, there are few representations that are more important than the oscillator representation, right? We will have Roger Howe here. That is like definitely the biggest authority on the subject, right? So yeah, for sure, it's a very important representation. It's just, I mean, it's not the one we choose here.
It's 1/4 plus 3/4, right? Mm-hmm. Okay, thank you.
Okay.
Another question? Okay, let's try Raul again.